Good afternoon, everyone. So we'll just wait for another 5 more minutes and we'll start the session. Okay. Good afternoon to everyone. Okay, I hope this is the strength. Fine. So, guys, what are we discussing in the previous session? What did we discuss in the previous session? Let me know in the Q&A. Everyone understood NLP, right? We have discussed about NLP. Everyone understood, right? Remember the workflow? Try to be active, guys. Fine. Okay, I see no one is responding. That's totally fine. Let's start the session, okay? Let's start the session. I'll start with the transformers in that case. Okay. Okay. So I'll just give an overview of NLP once again. So please listen carefully, everyone. So what exactly is NLP? Field of computer science, where we study how the computers can understand and process the human language. Correct. And what are the applications? Machine translation, chatbots, Q&A chatbot, sentiment analysis. Correct. Then comes the layers of NLP. What are the layers? Semantic analysis, phonology, lexicon, morphology, syntax, pragmatics. Correct. So what is this semantic analysis? It's the meaning of a data present in the document. Correct. Meaning of the data or the sentence present in the document. Okay. Present in the document. Example is here. Bank is located on the bank of a river. A financial bank I can say, a blood bank I can say. So it needs to understand the difference between this bank and also this bank of the river. Okay. Then comes the phonology. What is phonology? It's a study of sound. And then comes the lexicon, the vocabulary, which is present in the document. And the morphology. It is about the structure of the words. What is the structure of the word? Subject, verb, object, right? And like moving forward, we are having syntax and pragmatic. Syntax refers to the grammar, and pragmatics refers to how the language is being used in the particular context. And in the NLP, we have two main libraries. I think I mentioned it over here somewhere. Okay, I didn't mention. Okay, let me just mention it again. In NLP, we have two main libraries. Okay, the very first library is spacing, and the second one is NLTK. Okay, in the spacing, we will be having model wise, okay? Small, medium, large models, okay? In the space we will be having models, and in the NLTK is nothing but a natural language toolkit, okay? It's a toolkit where we'll be having all the methods, okay? All the methods of the libraries in these two main libraries, okay? And this is the difference between a corpus and a corpora. Corpus is a collection of documents, corpora is a single document. And we also need to know about the regex library. Regex is nothing but a regular expressions, which is mainly used to do the pre-processing for the data. And coming into NLP main components, we have the first one is tokenization. So tokenization is nothing but breaking down the text into smaller units. Okay, text into smaller units. It's called as tokens. Example: the session is from 10 to 12, so the tokens will be 1, 2, 3, 4, 5, 6, 7. 7 tokens. And then comes the stemming and lemmatization. Okay, stemming means it will return the base word. Lemmatization means it will return the root word. So the main difference between stemming and lemmatization is stemming will only cut the suffix, right? Only cut the suffix word. So it will return the base word, run. But in lemmatization, it will make sure that it is returning the root word, okay? And then comes the stop words. Stop words method. Examples of stop words are a, is, and, in, the, they, them. So these are some kind of a stop words, okay? So for example, let's say we are having a boy running and jumping in the park. After going through the stop words, the same we'll be getting as what we'll be getting. See, first it will go through lemma. So after going through lemma, running will be cut down to run, jumping will be cut down to jump. And after going through the stop words, we get all the remaining words of boy, run, jump, park. Okay. So that is about the stemming and lemmatization. In this, we are having two main functionalities, that is POS tags and NER. Okay. What is POS tags? POS tags is parts of speech. Noun, pronoun, verb, adverb, conjunction, interjunction, all the parts of speech which we have learned during our higher higher education, right? I mean during our schooling. And there is this another functionality called named entity recognition, which is mainly focuses on people, places, and the organization. Okay, people, places, and the organization. So, for example, Tim Cook is having a Google Pixel. In that case, it will remember the Tim Cook. It will identify it as a play people, Google Pixel as a phone. Okay, so phone it comes under a noun again. Okay, workflow of NLP here. So the workflow of NLP. Let's say I'm having a corpus. Okay, I'm having a corpus. So corpus is nothing but a collection of the documents. So what I will be doing is in order to build any NLP model, first I need to pre-process the data. So I'll make sure that all the multiple document information is being under one single document. Okay, is under one single document. Let's say that single document is new.txt. Okay, in the new.txt, I have combined all the data and I have stored it in the new.txt. So now what happens is initially I'll make sure that I'm converting all the words which are present in the document, the words which are present in the document into lowercase letters, okay, into lowercase letters. So here if you see, this is an example which is present in this. This is an, let's say this is the text which is present in new.txt, and I have assigned a variable called a for this file. So if I want to pre-process, first initially I will convert them into lowercase. Then I will apply the regular expressions for what to clean the document. To make sure the document is clean, I will apply the regular expressions. If there is a pattern being followed, hashtag sin or else hashtag same, like followed by hashtag, we'll be having some words, right? If it is related to a film or else if it is related to any other social content, correct? And also if there were any patterns such as at the rate of Gmail, I just want to replace it with email. So we can do replace, or else we can directly replace it with an empty space like this. Or if you want to replace it with some one single space character, so we can do that. Okay, we can do all that cleaning process. So after cleaning the text, then we will be dividing them into tokens. Then we'll apply the stop words and stemming and lemmatization. See, these two steps we can either do, okay? It's like we can either first do stemming or lemmatization, then go to stop words, or else we can either apply stop words first and then go to stemming or lemmatization. Then if you want to work on the functionalities, pivot tags are in here, we can work on these functionalities, or else we can directly go with the word embeddings, okay? Word embeddings, you all know, word to vec, cbow, c, gram, okay. So word to vec is nothing but converting a word to vector, right? Fine. Clear everyone? Clear? Okay. Thank you. If you're still having a doubt, please let me know at the end of the session, okay? For the last 10 minutes, I'll just spare some time related to this covered content in this session, okay? So in that last 10 minutes, you can now ask the doubt and I will repeat the things once again, okay? Fine. So now we will discuss about this evolution of this chatbots, okay? Evolution of chatbots we'll discuss. How the chatbots got into the picture and what are all the chatbots which are available, and right now what chatbots are currently in the picture, okay? We'll just discuss them and then we'll move into the transformers architecture, okay? So initially during the early 2000s we used to have rule based chatbot, okay? We used to have rule based chatbots, and if you're having any queries related to the topic which I'm saying, ask me in the Q&A, mention the topic, okay? Because I see no one is responding in the Q&A also, so I'll be just proceeding with the content. If you're having doubts, please let me know in the Q&A. So rule based chatbot. So how the rule based chatbots work? So rule based chatbot they work on the predefined rules, or else the if else logic which were predefined. So if a user is asking about this query, just reply him with this particular content. So it's like there is already a predefined reply which is present in the code, which is predefined in the code. So as per the user query, it will just drop the same reply. So those kind of chatbots are present in earlier 2000s. Okay, rule based is nothing but predefined answers or rules. We can say rules. And later we are having this NLU. NLU is natural language understanding. Okay, NLU is natural language understanding, and in the NLU we are having RASA chatbot. Okay, RASA chatbots. Anyone aware of this RASA chatbot? Anyone heard of RASA chatbot? Okay, fine. Thank you. I see the response. Thank you. So from now, please listen carefully. Okay. In the RASA chatbots, we have intent. Okay, intent or intents. Okay, we have intent or intents. So first, we'll pick the category. So let's say the category is related to greetings. Okay, greetings. So here, this is the intent. Okay, this is the intent. Let me just write here intent. So each and every intent will have question and answer. So each and every intent will have question and answers. Q and A. Okay. So I'm saying greeting category is my intent. So Under this category, I will have question and answers. So under greeting, what kind of questions I can get? How are you? How are you is one kind of question. WhatsApp is another kind of query. I can get WhatsApp or with WhatsApp. This kind of in this current trend, mostly everyone will be asking this, right? So how are you, WhatsApp, and what kind of other questions I can get? Good afternoon. So that is one kind of greeting, right? Good afternoon is one kind of greeting. So let's say these are the kind of the questions which are being present under this greeting intent. Okay. So as we are having questions, similarly, for each question we'll have the answers also. Let me just keep here push for each question. So for how are you, it will be I'm doing good, right? Let's assume, okay. Even if you're not doing well, let's assume that we are doing good. I'm doing good. WhatsApp, everything well, everything going well. Or else we can directly reply as nothing much, nothing much. Good afternoon. Yeah, the reply will be the same. Good afternoon. Good afternoon. How is your day? Okay, these are kind of the replies. Okay, now understand for for these three questions, these are the kind of the replies we can expect. Okay, and this is a greeting intent. This is the greeting category. So if any time, so one question can be asked in many formats. Correct. One question can be asked in many formats. See, everyone will be getting the same row, but the format they were trying to ask the question will be different, right? Some will be directly asking the question by mentioning the terminology. Some will be going around and asking the question. Some will be explaining the content and what exactly they were trying to understand. They'll be asking the question in that format, right? So here also, let's say this category is greetings, right? Under the greetings, we're having question and answers. Three questions. For each question, there is an answer. Okay. So now the user is coming up and asking like, how is your day? Okay, how is your day? User got up and asked a question like, how is your day? So now, as this is a NLU chatbot, natural language understanding chatbot, it will understand that the query is related to greetings category. It is related to greetings category and it will pick up the best possible answer. Okay, how is your day? Like, good afternoon. So the query input query was, how is your day? It's like nothing much, or else you can go for I'm doing good. Correct. These two are the most expected replies, right? So, are you getting now how exactly intents, what intents are? Intents are greetings, okay? Intents are greeting, or else if you are building a travel chatbot, you can consider the top five cities, cities as an intent, and locations, yeah, locations you can consider instead of cities, and the travel itinerary planning, scheduling. See, intents are basically the category, and under the category we have questions and answers. Or at least this we'll be calling it as one intent. Okay, greeting is called as one intent. So for each and every intent, we'll have at least four questions and four different answers for four different questions. So what is the main difference between this rule based and NLU? Here, one question, one answer. Here we are having three different questions and three different answers. And if the user comes and asks a different query also, it will make sure it is answering the nearest possible answer. And how it is working based on the intent tense. Okay. And this is about the Rasa chatbots. I hope Rasa chatbot is clear for everyone. Yeah, hotels, Airbnbs. Thank you. Okay. Thank you. Okay. So along with this Rasa chatbot in the picture, How many of you remember IBM Watson chatbots? IBM Watson. Even IBM also got this IBM Watson chatbots. They were very famous. Okay, they were very famous. IBM chatbots. Fine. So now, moving forward, we got chatbots from RNN. But RNN is struggling with what kind of issue? RNN is struggling with what kind of issue? Okay, it's fine, Monica. RNN is struggling with what kind of issue, guys? The RNNs are struggling with what kind of issue? No, it's always recurrent. Okay, but I just want the exact term. Okay, I want the exact term. Even with RNN also, we can build the chatbots. I gave you an example also, next word prediction. But I told you they were struggling with some issue, and because of that issue only, LSTM got into the picture. I told, right? Because of RNN issue only, LSTM got into the picture. What is the issue RNN are struggling with? Okay, fine. I'll just see. RNN was struggling with the long-term dependencies, right? Long-term dependencies. And what was the issue called as? Vanishing gradient issue, right? Vanishing gradient is the issue. RNN are struggling from the long-term dependencies, and that kind of issue is known as a vanishing gradient issue. Even the gradient is vanishing. Okay, and now then LSTM got into the picture. And what does LSTM do? LSTM was able to handle the long-term dependencies, but it is unable to remember the context. Okay, it is having an issue with the context. Context is nothing but understanding the meaning of the input, right? Understanding the meaning of the input. The main issue with LSTM is it was unable to understand the meaning of the input exactly. If I am giving an example as a bank of a river, so it is unable to understand which bank I am referring to. Am I referring to a bank of a river or is it financial bank I am referring? It was unable to understand the context. The context issue we are having in LSTM. So to resolve this, here comes the transformers architecture. Okay, transformers architecture. I'll just pull up a new tab. So transformers architecture. Anyone heard of this transformers architecture? Anyone heard of transformers architecture, guys? Okay, and if you feel like the session is boring, let me know. Okay, if you feel like the session is boring, let me know. Let's try to keep some small quiz in between. Okay, because I see many of the blank responses, so only few people are answering all the thing, all the answers. Okay, fine. But this transformers architecture is very important if you want to understand how the ChatGPT or else Gemini is working. Okay, understanding transformers architecture is very important. Okay. Okay, fine. So this transformers architecture work based on the self-attention mechanism. They work purely on the self-attention mechanism, and they will make sure that they were purely to understand the context. Okay. purely understand the to understand the context. This transformers architecture or this architecture, it works based on self-attention mechanism, and it is developed purely to understand the context because LSTM was struggling on the context issue. Correct. Okay. So, but when did this transformers architecture came into the picture? Transformers architecture came into the picture in the year 2017. Okay, 2017. And about this transformers architecture, everything was detailedly explained in a research paper which is published by Google. Okay, and the paper name is Attention is All You Need. Okay, Attention is All You Need. It is a paper published by Google DeepMind. Google DeepMind. Okay, it's a research paper. It's a research paper. So remember transformers architecture, and it mainly works based on the self-attention mechanism. And the main aim of this transformers architecture is to understand the context. And in 2017, in the paper Attention is All You Need, okay, which is published by Google DeepMind, it is written about this transformers architecture. Okay, and in this transformers architecture, we are having key components also. Okay, we have key components. We have key components in this transformers architecture. The first one will be the encoder, decoder, positional encoding, and attention mechanism. Okay, so rule-based chatbot, NLU, IBM Watson, RN and LSTM. Then comes the transformers architecture. In the transformers architecture, it works based on the self-attention mechanism. The main aim of it is to make sure to understand the context. And in the paper, Attention is All You Need, which is published by Google DeepMind, which is a research team. In the year 2017, it was written everything in detail about this transformers architecture. And the key components of this transformers architecture are encoder, decoder, positional encoding, and attention mechanism. I hope it's clear until now, everyone. And coming into this multi-head attention and feed-forward neural networks, we'll be discussing later. But the main components are encoder, decoder, positional encoding, and attention mechanism. Is that clear, Rohini? Okay, let me just share my PPT screen. Okay, just give me a minute. I'm sharing my full screen. Okay, just a minute. Just confirm me when you're able to see. And also, let me just open the OneNote also along with this. So everyone able to see the screen, right? And I hope until now everything is clear. Okay, so now we need to discuss about the transformers architecture, right? Just give me a minute, just a moment. I'm sorry, I just got a call. I'm sorry for that. Okay. So what are we discussing? We are discussing about the transformers architecture, right? And what is the paper that was published? Attention is all you need. Okay. Now we'll just dive into this. So the main agenda of these transformers, what we'll be learning in this PPT is we'll be learning introduction to transformers, which is already done. I just gave a short intro, right? Just a minute. So guys, in the meantime, please just go through the topics which we have covered. Okay, just give me 2 minutes, please. Okay, I'm sorry. Okay, so transformers introduction is done. We'll just deep dive into the transformers and the key components. What are the key components? Encoder, decoder, and what are the other two? Positional encoding and self attention, right? And also we'll understand each and every key component. And moving further, there is this summary for that. Okay. Okay. So just consider this. There is an input, there is an output, and there is this transformers. Okay. So what exactly happening? Whatever the output task this transformer is prepared for. Okay. So let's say this transformer is able to handle only the language translations. So it will just consider the input, it will do the language translation, and it will do the give the output. And if this transformer is built for summarizing purpose, it will give the input. We should give the input. Transformers will summarize that output, or else it will summarize that particular input, and it will provide the summarized output as a text. So this is how the transformers work. But in this block which you see lies the encoder and the decoder. Okay. And if you see here, they are the neural networks which are specifically designed for sequence transduction task, meaning they can transform an input sequence into an output sequence. Whatever the input sequence it is, as per your query or else as per the transformers which is trained on for a specific task, it can do that particular translation. Okay. And what exactly happened inside this encoder and decoder and in this black box, we'll just see. Okay. So key components. See here, there is an input text. This is the transformers architecture, and here we are getting the output. The input text is how are you, and it is going into the transformers. We are getting the output as coma estas. Correct. And in between, what is the process happening? There is a decoder and an encoder and decoder. Correct. And also, we will also get this positional encoding and attention mechanism. But initially, the main process is input will go into the encoder, that will pass into the decoder. Again, encoder will be doing the encoding things, and the final from the final layer, it will push to the decoder, and from the decoder, it pushes the output. It will give the output. So this is what exactly happens in the transformers. Fine, encoding the things, decoding the things, giving the output. But we'll see how exactly the architecture is. Okay? This is what the exact architecture is. This is what the transformers exact architecture is. So now I'll just give you 2 minutes, everyone. So what are you understanding by looking at this picture? Okay. I don't want any Google answers. I don't want any summarized ChatGPT answers. Okay. Just what your understanding, explain me. Okay. By looking at this architecture, what your understanding, explain me. Okay. Now everyone, I want everyone to look through that architecture and understand how the workflow is happening. Until now, you understood that there is an input and which is encoded, and again it is sent into a decoder, and from the decoder we are getting the output. That is what we have seen. But in the complete architecture, what are the things that you're seeing and what are you understanding? Let me know. Okay. So anyone understood anything? What exactly is happening over there? Even if you're not understanding anything, it's totally fine. So let me give my point of view, okay? See, let's say even I am learning, okay? Even I am learning the architecture. So what I will understand by looking at this, what I will understand, okay, there is this input sequence. Okay, two sides, it is divided into two sides, encoder and decoder. Okay, this red box is encoder and this one is the decoder. And first, the encoder things will be happening. Input, encoder, decoder, output. So there is an input sequence. So that could be an input to the encoder, correct? And in between directly, the input is not going to the encoder. There is this embeddings and also positional encoding happening. And after that only it is going into the encoder. And in the encoder, we are having multi-head attention, adding and normalization, multi-layer perceptrons, again another layer of normalization, and then from there it is going into the decoder. Okay, and in the decoder it's directly going into the multi-head attention, and also along with that there is a target sequence, what exactly that we are expecting, and the embeddings. There is this marks to multi-head attention, normalization again. I mean, something is happening over here in this decoder, and we're getting the output through the activation functions again, softmax. Correct. This is what I can decode. Were you able to decode this? Were you people able to understand those things which I have just explained? See, by looking at the image, those are the things which we can understand, right? We can grasp, right? So now we will understand in detail of what exactly this input sequence is. Input sequence is nothing but, I just take you to one more time, or else let me just stop here. Understood until now, just by looking at the image, understood what exactly present in that image. By looking at that particular architecture, did you understand? I mean, I'm not saying you to understand all things. The workflow, did you understood? There is an input sequence which is going into encoder, and before going into encoder, it needs to go through embeddings, positional encoding, then encoder decoder output. Okay. Today we'll discuss about that input sequence, embeddings, positional encoding. What are the encoding layers present, decoding layers present? Okay. I hope it's clear for now. Whatever the things which you're hearing. So let's have a short break for 10 minutes. Okay. So be here by 3:05 or 3:06. Okay. Let's have a short break. And after the break, we'll discuss about the Transformers architecture. In the meantime, if you're having any doubts, you can post it here in the Q&A. Okay, I hope everyone is here. Okay, let me just share the full screen and we'll discuss about this input sequence embeddings. Okay, and then the embeddings we are also having types. Okay, we'll discuss about all those things. And please make sure that you are listening to the session properly. This, if you are understanding this transformers architecture, you will understand how the ChatGPT is working, how Gemini is working. Let me just share my full screen. Just a moment. Okay. So now input sequence embeddings. So let's say the input sequence sentence is the cat sat. Okay. Okay, the cat sat. Let me just write it in the notepad. Input sequence. The cat sat. Okay. The cat sat is the sentence. Okay. The cat sat is the sentence. Now, after this input sequence, it is going into embeddings. Okay. After this input sequence, it is moving into the embeddings. And this embeddings also, inside this embeddings, we're having multiple types. Okay. We're having multiple types in this embeddings. So now I'll write one by one what are those. Okay. In the embeddings, after input sequence, it goes into embeddings. And inside the embeddings, we're having token embeddings. So we're having token embedding. And also we're having linear transformation. Linear transformation. And also along with this, we're having scaling. Okay. Scaling. Then we are having weighted sum of values. Okay, weighted sum of values. And mostly while playing this linear transformation only, the scaling, the weighted sum of values will be occurred in that process. Okay. So first we'll discuss about this token embeddings. What is this token embeddings? Okay. Token embeddings. Okay, token embeddings. So I said this is our input sequence, right? This is our input sequence. The cat sat is the input sequence. So as per NLP, whatever the input is, it will be divided into tokens. Then the text will be processed, right? So now the cat sat sentence will be divided into tokens. The cat sat. Okay. So how many tokens are we having here? 3 tokens we're having here. 3 tokens we're having. In this token embeddings, first it will be divided into tokens, and each token, okay, for each token, a token embedding will be assigned. Each token, the token ID, I mean, it will be embedded. Before embedding, the token ID is assigned. Okay, the token ID is assigned. So we just take to one more. So what was the sentence again? Cat sat, right? Just let me write it again. So this is a sentence, correct? So now initially this is the input sentence. This input will be passed into what? It will be passed into the embeddings, right? Embeddings. That input sentence will be passed into embeddings, input sequence. This is the input sequence. Now what exactly happens in the embeddings? In the embeddings we're having embeddings. In the embeddings we're having token embeddings first, right? Token embeddings we're having. We're having token embeddings. In the token embeddings, first initially it will take this whole sentence, the cat sat, and it will divide them into tokens. So how many tokens we get? The cat sat. 3 tokens, right? So for each token, the token ID will be provided. Okay, token ID will be provided. So and randomly it will be assigned. Okay, so it could be 101, 102, 103. So these are the random token IDs which are assigned. Okay, the random token IDs which are assigned. So why this token ID is needed? These are all token ID. Okay, token ID. Why token ID is needed? These are the tokens. Why the token ID is needed? Anyone having any answer? Anyone want to answer why the token ID is required over there? Why the token ID is required? Because if you see here, everyone seen able to see the screen, right? A neural network designed that utilizes the self-attention mechanism. Up to here, neural networks. So what is the input that neural networks understand? Neural networks. Neural networks will understand only number as an input, right? They will understand only the number, right? They will be able to understand only the numerical input. If I'm giving the textual input, they won't be understanding anything. Correct. They won't understand anything. They will understand the numerical input. So to make sure that the input which we are giving is being understood by this neural network. So we are adding this, we are creating this token IDs. Okay. So token ID is acting like a bridge between a textual data and the numerical data. Converting the text data to a numerical data, converting that to a numerical data, it is acting as a bridge between textual to numerical. Understood now? As the token IDs are necessary because the neural networks cannot operate directly on text. They work with numbers. So these token IDs will act as a bridge between text and the numerical data. Okay. I hope everyone understood why the token IDs are required. Yeah, to identify the okay, fine. So now that we know what exactly happening over here, we just got to know why the token IDs are created. Correct. So the token ID for each token, the token ID will be created, and for each token ID, we have the dimensions. Okay, we have a vector for each token. For each token of the token ID, we have vectors. What will be the size of the vector? 512 dimensions. Okay, 512. And even for this token also, it is 512 dimensions. And even here also, it is 512 dimensions. So what are these 512 dimensions for each and every vector? For each and every vector, what are these 512 dimensions? What are the? Let me make it clean and clean. I see someone raised their hand. Yeah. So what are those 512 dimensions? What exactly each dimension is saying about? Can I get any answer? What are those 512 dimensions? I don't want any ChatGPT answers, okay? So how many tokens are we having here? We are having 3 tokens. And for each token we are having 512 dimensions. Right? Each token we are having 512 dimensions. Okay, fine. Let me just resolve that to show also. So each token for the we are having 512 dimension vector. For cat we are having 512 dimension vector. For sat we are having 512 dimension vector. But for one single word, why do we need this 512 dimensions? Okay. That I'll just write down over here. Okay. Sorry, it's 512. Why do we need 512 dimensions? So 512 dimensions are nothing but the 512 features. Okay. 512 dimensions are nothing but 512 features. And they capture the information about the meaning of that particular token. Okay. Context of that particular token and the relationship with the other tokens. Okay. Relationship with other tokens. So in these 512 dimensions of 512 features, each and every feature will capture one kind of relationship. So one feature could be, or else one dimension could be capturing the meaning, the other dimension could be capturing the context, the other dimension will go for the relationships with the other tokens. So that we are having around 512 dimensions, 512 ways of describing the token. Okay, it's like 512 ways of describing the token. Describe the token. Okay, token or the token ID, you can say token ID. Let's consider token ID. Understood what exactly 512 is doing over here now? Understood everyone? What 512 is doing? Okay, no response. Fine. Okay, I just have one small query. I'll just stop the screen share so that you can answer. So why exactly 512? 512 dimensions I'm considering. Why not more or why not less? Why exactly 512 dimensions I'm considering? Why not more or why not less? Try to think. I'll just give you 1 minute, okay? Try to think of it and let me know. Why only 512 dimensions? Why not more than 512 dimensions or else less than 512 dimensions? Not the correct answer I was expecting. No. Thank you. Thanks for answering. But it's not correct, okay? 512 words of bytes in memory storage. No. 512 means dimensions, okay? How 1D, 2D, see, human being will be able to see how many dimensions? Dimensions, right? So, in a similar way, here we are having 512 dimensions, okay? 512 dimensions. It's not like words or bytes which are stored in the memory, okay? And why only 512 dimensions? Why not more than 512 or less than 512? Now we'll discuss about that, okay? And remember, 512 is nothing but the size of a vector. 512 is the size of the vector of the token, or is the token of that particular token, okay? But remember, 512 is the size of a vector. 512 features, or else 512D is the D model, or else we can say D model also. Dimension model, the model dimensions. D represents dimensions here. D represents dimensions, okay? So now, why not less dimensions, okay? Why not less than 512? Less than 12, yeah. So now everyone understood what these dimensions are. They try to capture the information, right? So why not less than 512? Now we'll see if you're having less than 512. Less than 512, okay? Less than 512. What happens if you're having less than 512? So if you're having less than 512, what happens is it will not be able to represent the meaning well, okay? It will not be able to represent the meaning well. So the best example is there is an input query, describe person, okay? Describe person. So this is the input query. So let's say if I'm having two dimensions, so if it is describing the person, how many things it will be capturing? Only two different types of things it will capture. Either the meaning it will capture, or either the relationships it will capture, either the context it will capture, right? From these three, any of the two things only it will capture. One thing it will be missing out. So if I give input as describe the person with the three words or two words, it will just give the person name with good and followed by the other thing, whatever the dimension it was storing, correct? But let's say there is a huge difference between this 512 and 2D, because two dimension means only not more than two words it can describe the person. But if I am giving describe the person with 512 dimensions, in that case it will have 512 adjectives, like 512 different ways to describe this single person. Correct. To describe this single person, it will have 512 different relationships, 512 different meanings. Clear? Understanding? So it's better to consider 512. Even to build the transformers architecture, it was considered only 512 dimensions. Okay. Okay, I didn't share my screen. Fine. I'm sorry. I'll explain it once again. No problem. Okay. So let me write again. Describe person well. Okay, fine. So let's say initially we are considering 512 less than 512 dimensions, right? So if you're having less than 512 dimensions and if we write describe a person, so now what happens is let's consider less than 512, right? We are doing only two dimension, let's say two dimension. So to describe a person in this two-dimensional, it will store only two things. Either it could store the meaning in one dimension, and in other dimension it could store either the relationship or else the context, right? So if I give this as an input, it will just tell about that person in two words, correct? In two words, it will tell in two words. But if I do consider, but if I do consider 512 dimensions, it will have 512 different ways, 512 different adjectives to tell about this particular person, correct? So 512 different relationships it will consider to tell about this particular person. So that is the reason we are considering this 512 dimensions, okay? Even to build the transformers architecture also, they have considered the 512 dimensions. So that is the reason we are not considering not less than 512, okay? We're considering 512. So now you may get a query like, why not more than 512? Why not more than 512? So if we are having more than 512 dimensions, what happens? Overfitting is the main thing, right? Overfitting may happen. And the other thing is the training process will be slowed down, right? Training will be completely slow down. And what could happen? There it could take up a huge memory, huge computational power, huge memory. Correct. So in order to make sure there is a balance between all these things, the 512 is the base which is considered, okay? 512 is the base which is considered. Understood now? Understood now, everyone? Any doubts, anyone? Anyone, any doubts? I think continue, right? So until now we have seen about these dimensions, right? And there were few models also, like uh, BERT model, okay? I know you people have heard about this BERT, 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 okay? In the BERT only we are having two different variations. One is the base model, and for the same BERT we are having large model also, large model. And for the base model, they have considered 768 dimensions, okay? And for the last, they have considered 1024 dimensions, okay? 1024 dimension. And it also depends on the size of the data that you're having, okay? And for GPT-2, they have considered again 768 dimensions, okay? Okay, these are some of the D models or the dimensions which are considered for different models. And so, depending on our model size, we can change the dimensions, okay? We can change the dimensions. And but 512 is a default choice, okay? 512 is a default choice. So for this on the cat 512 dimensions, what exactly happens is, so for the it's 101, right? So for embedding the output will be 1010 and continuing up to 512 dimensions, okay? First dimension, second dimension, third dimension, fourth dimension, Okay, up to 512. Up to 512. Okay, up to 512. And similarly, for the embedding cat, we have the same something but 0, 1, 0, 1 up to 512. And for SAT also the same. Okay, SAT also it will be the same. So when someone asks you what is the embedding size of each token you have considered, you can say 512 dimensions. Okay, fine. So this is about the token embeddings. Okay, we did we write here. We are done with token embeddings. Okay, in the token embeddings we are done. Now we will discuss about this linear transformation. Linear transformation. In the linear transformation, what we'll do is we will create the Q, K, and V. Okay, we'll create Q, K, and V. What are those Q, K, and V? Now we'll see. Okay, let me just write here. We'll have Q, we'll have K, we'll have V. What is Q? What is K? Q is nothing but query. Okay, Q is nothing but query, or else query vector also we can say query vector. Okay, what does the query vector do? Query vector will help us to calculate and understand the importance with the other token. Okay, calculate and understand the importance with the other token. Okay, other token. Remember this. Q is nothing but a query vector, and it will help us to calculate and understand the importance with the other vector. And similarly, we are having a K. K is nothing but a key vector. K is nothing but a key vector. What does the key vector do? So now the key vector will help us to find the attention scores with the token. Help us to find the attention scores with the tokens. Okay? With the tokens. So now we are having left with V. V is nothing but the value. What does value do? Value is nothing but the actual value after the word embedding. Actual value after the word embedding. So in linear transformation, what we do is we'll create these Q, K, and V vectors. Okay, Q, K, and V vectors. What is Q? What is K? And what is V? Q is nothing but the query. K is nothing but the key. V is a value. We will create query key and the values. Okay. We create query key and value. And how we will create? By multiplying the weights. Okay. We'll consider the inputs, whatever the token ID embeddings we are having. We'll multiply them with the weights of this Q, K, and V. Let me just write here. These inputs. Okay. These embedding dimensions, whatever we are having, that we will be multiplying with this weights. Okay, with the weights of this. So for query, what will be the query weight? So for query, it will be weight of Q. Okay. For key, it will be weight of K. For V, it will be again the weight of V. Okay. So these are the weights. Okay. These are the weight values. For query, it is WQ. For K, it is WK. The value, it is WV. Okay. The weights will be assigned. The weights will be assigned and it will be multiplied. Okay. Multiplied with the input embeddings or the token embeddings. Token embeddings. Okay. So how it will be happening for query? Again, it will be X over here. For key, again, it will be X over here. For V also, it will be again X here. So let's consider the input token embedding is for the. Okay. The we are considering. So here X is the, in that case, for that whole 512 dimension, a randomly assigned weight of query will first initially be multiplied and it will be calculated and it will be getting some value and it will be going through the training process. And if there is a need to adjust the weights, again through the back propagation, the weights will be adjusted. Okay. Again through the back propagation, the weights will be adjusted. So here what is X? X is nothing but the token embedding. And what are these WQ, WK, and WV? They are the learned weights. Okay. They are the learned weights. Let me just write here. WQ, WK, WV are learned weights. Okay. WQ, WK, WV are the learned weights. And for these weights, initially they were randomly assigned. Then through the back propagation, the weights are adjusted. Okay. The weights are adjusted. And what is X here? X is nothing but the token embeddings. Token embedding. Okay. And what are we doing over here? In this process, what are we doing? We're computing the self-attention weights. Okay. We compute the self-attention weights. How are we computing? For each and every embedding, we add that particular query weight, we add the particular key weight, we add that particular value weight. By adding these weights, we'll be assigning the self-attention weights, and then we'll be getting in the output we get Q, K, and V, right? Q, K, and V. Understood what's happening in linear transformation? Understood what is happening in the linear transformation? After that, the scaling and the weighted sum of values will be happening. Okay. Let me know. Linear transformation is important. I have created a poll. Let me know. I see one no. Only 16 people have attempted the poll. I see one no. So please let me know in the Q&A. What did you didn't understand? As I'm not sharing my screen, you can ask me directly. So please ask me what did you not understood. Okay, the transformer part. See, we are still getting into the transformer part. Okay, we are still getting into the transformer part. We didn't even start with the transformer part. Token topic. So what? How we are dividing into tokens or the token ID? You're saying? See, guys, we're still at here only. We're still here only. Just a minute. Let me just share the screen and show you. This is good. See, we are still at here only. Embeddings only. We didn't go into the encoder. We are at embeddings only. In the embeddings only, we are having this linear transformation. We need to go through the positional encoding. Then comes the encoder. Then comes the decoder. Then the output. Okay. And what was the token topic you didn't understand? Yeah, the tokens are same. Okay. The tokens are same. Just like how we are in the NLP, just like in the NLP, how we are having the tokens, those are the same tokens. But here, for each token, in order to make sure the networks, the neural networks are understanding the numerical concepts, the token ID is assigned to them. Okay, the token ID is assigned to them. And for each token of the token ID, we have 512 dimension vector. Is your doubt clear? I mean, was your doubt cleared, or else still you're having any doubt on any specific topic? I see two no's, so that is the reason I'm asking. Yeah, fine. So I'll just conclude this for today, okay? I'll just conclude this for today. If you're having doubts, ask me. Okay. If anyone is having any doubts, ask me now. Yeah, I see someone raised their hand. Yeah, Darshan. Are you having any doubt? Okay. Anyone, any doubts in understanding any topic in today's session that we have discussed? You may ask you may ask here, okay? And if you're not having any doubts for today, you may leave the session. Thank you. Thank you, guys. Thank you, Darshan. Thank you. So for today, you may leave the session, guys. Thank you. Thanks for attending. Any doubts, anyone? Hope it's clear. So if no one is having any doubts, I will end the session now. Thank you for attending. And tomorrow we'll see the mathematical implementation also regarding this Q, K, and V. Okay. Thanks for joining. Thank you, guys. Thank you.